The stellar fireworks show of 2024, T Coronae Borealis' explosive encore. Get ready to witness a spectacular celestial event. The star system T Coronae Borealis, TCRB, is on the verge of a dramatic outburst, predicted to occur by September 2024. This isn't just any star. TCRB is a unique pair of stars known for their explosive displays called nova eruptions. These cosmic fireworks promise to be a breathtaking sight, even visible to the naked eye. But what exactly are novae, and why is TCRB so special? Let's dive into the fascinating world of stellar explosions and learn all about this exciting upcoming event. Meet the stars of the show, T Coronae Borealis, a dynamic duo. T Coronae Borealis isn't a single star, but a pair of stars dancing together in space. Imagine two partners twirling on a dance floor, but instead of music, they're driven by the force of gravity. The red giant, a puffy old star. One of the partners in this stellar dance is a red giant. Think of it like a grandpa star, big, old, and a bit puffy. Red giants are stars that have used up most of their hydrogen fuel, the stuff that powers their nuclear fires. As they run out of fuel, they start to expand and cool down, turning into these enormous reddish stars. The white dwarf, a tiny super-dense star. The other partner is a white dwarf, the opposite of a red giant. White dwarfs are small, compact stars about the size of Earth, but don't let their size fool you. They are incredibly dense, packing a mass similar to our sun into a tiny ball, a cosmic tug-of-war. These two stars are so close together that they orbit each other very quickly. It's like a cosmic waltz, but with a twist. The white dwarf, with its stronger gravity, is constantly pulling gas away from the red giant. It's like a cosmic vampire, slowly draining its partner's life force. The nova explosion, a cosmic light show. As the white dwarf star siphons off gas from the red giant, it builds up a layer of material on its surface. This layer gets hotter and denser over time, like a pressure cooker on the stove. Eventually, the pressure becomes so intense that it triggers a massive explosion, a nova. During a nova explosion, the white dwarf star blasts out a huge amount of energy and material into space. The star system suddenly brightens dramatically, becoming thousands or even millions of times brighter than usual. This outburst of light and energy is what we call a nova, a recurrent nova, the star that keeps exploding. T Coronae Borealis is a special kind of nova called a recurrent nova. This means it has multiple outbursts over time, unlike most novae that only explode once. Why does TCRB keep exploding? It's because the white dwarf star is constantly pulling in new material from the red giant. Each time it accumulates enough material, it triggers another nova explosion. It's like a cosmic firecracker that keeps going off. The science behind novae, atomic fireworks. To understand what's happening during a nova explosion, we need to dive into the world of atoms. What are atoms? The building blocks of everything. Atoms are the tiny building blocks that make up everything around us, from the air we breathe to the stars in the sky. Each atom has a center called a nucleus, which is surrounded by even smaller particles called electrons. Nuclear fusion, the power of the stars. Inside stars, atoms undergo a process called nuclear fusion. This is when two or more atoms join together to form a new heavier atom. This process releases a tremendous amount of energy, which is what makes stars shine. In the case of TCRB, the white dwarf star's gravity pulls hydrogen, the lightest element, from the red giant onto its surface. As the hydrogen builds up, it gets compressed and heated until the nuclei of the hydrogen atoms start fusing together to form helium. This fusion reaction releases an enormous amount of energy, causing the nova explosion. The expanding shell, a glowing remnant. The energy released during a nova explosion blasts out a shell of gas into space. This shell expands outwards, glowing brightly as it interacts with the surrounding interstellar medium. This glowing shell is what we see as the nova through telescopes. The expansion of the shell also reveals clues about the composition of the ejected material. Scientists can analyze the light from the shell to determine what elements were created during the explosion. Novae are important factories for creating elements heavier than hydrogen and helium, including elements like carbon, nitrogen, and oxygen, which are essential for life. The 2024 nova, a front row seat to a stellar explosion. The next nova explosion of T Coronae Borealis is expected to be a spectacular event. While the exact timing and brightness are uncertain, astronomers predict that it could occur by September 2024 and potentially become as bright as the North Star. This would make it easily visible to the naked eye, even in light-polluted areas. Imagine looking up at the night sky and seeing a new bright star suddenly appear. That's what the TCRB nova could look like. It would be a rare and exciting opportunity for everyone to witness the power and beauty of the universe firsthand. How to observe the 2024 nova? If you want to see this cosmic fireworks show, here's what you need to do. Location. TCRB is located in the constellation Corona Borealis, the northern crown, which is visible in the northern hemisphere. Use a star chart or app to find its exact location in the sky. Timing. Keep an eye on astronomy news and websites for the latest updates on the nova's progress. Once the outburst occurs, you'll have several days or even weeks to observe it. Viewing tips. Find a dark location away from city lights for the best view. If you have binoculars or a telescope, use them to get a closer look at the nova and its surrounding nebula. Be patient. The nova may take a few nights to reach its peak brightness. The nova family. A spectrum of stellar outbursts. While all novae involve a white dwarf accreting, gathering material from a companion star, the specific details and outcomes can vary significantly, leading to different classifications. Classical novae. The most common type of nova, brightness increase, typically brightens by over 12 magnitudes, becoming thousands of times more luminous. Energy source, runaway thermonuclear fusion of hydrogen on the white dwarf surface. Remnant. The white dwarf usually survives the explosion, although it loses some mass. Recurrence. Most classical novae are thought to be recurrent, but with long intervals, thousands to millions of years, between eruptions. Recurrent novae, RN. Less common than classical novae, brightness increase. Typically brightens by about 9 magnitudes. Energy source, similar to classical novae, but with a faster accumulation of material on the white dwarf, leading to more frequent eruptions. Remnant. The white dwarf survives, but its mass may gradually increase with each eruption. Recurrence. Eruptions occur on timescales of decades to centuries. T. Coronae Borealis is a well-known example of a recurrent nova. Dwarf novae. Different from classical and recurrent novae. Brightness increase. Typically brightens by 6 magnitudes. Energy source. Not due to nuclear fusion, but caused by instabilities in the accretion disk surrounding the white dwarf. Remnant. The white dwarf is not significantly affected by the outburst. Recurrence. Eruptions can occur on timescales of days to months. Other types of nova. Symbiotic novae. These involve a white dwarf accreting material from a red giant star in a wide binary system. They are characterized by slow brightness changes and long eruption durations. Luminous red novae. Thought to be caused by the merger of 2 stars, these are much rarer and more luminous than classical novae. The importance of studying novae. Each type of nova provides unique insights into different astrophysical phenomena. Nucleosynthesis. Novae are factories for creating heavier elements such as carbon, nitrogen, and oxygen, which are essential for life. Stellar evolution. They offer glimpses into the late stages of a star's life and the complex interactions in binary star systems. Accretion physics. Dwarf novae help us understand how matter accretes onto compact objects like white dwarfs. Galactic archaeology. Novae can serve as distance indicators, helping us map the structure and evolution of our galaxy. By studying the different types of novae, astronomers can piece together a more complete picture of the universe's diverse and dynamic nature. The red giant in the T. Coronae Borealis TCRB system, like all red giants, has a fascinating and complex composition that reflects its stage of stellar evolution and interactions with its companion white dwarf star. Core. Helium. The core of the red giant is primarily composed of helium. This helium is the ash left over from the fusion of hydrogen, which was the star's main source of energy during its main sequence phase, when it was similar to our sun. Degenerate core in later stages. As the red giant evolves further, the helium in the core starts to fuse into heavier elements like carbon and oxygen. Eventually, the core becomes so dense that it enters a state called electron degeneracy, where the pressure from electrons prevents further collapse. Inner layers. Helium-burning shell. Surrounding the core is a shell where helium is actively fusing into carbon and oxygen. This fusion process generates energy that powers the red giant. Outer layers of hydrogen. The outer layers of the red giant are still primarily composed of hydrogen, although some of it has been converted to helium through fusion in the past. Other elements, the outer layers, also contain trace amounts of heavier elements like carbon, nitrogen, and oxygen. These elements were either present in the original star-forming cloud or were created through nuclear fusion in the core and later dredged up to the surface. Losing mass. The red giant is in a phase of its life where it's losing mass at a rapid rate. This mass loss is driven by strong stellar winds and the gravitational pull of the white dwarf companion. The expelled material forms a vast envelope of gas and dust around the star system. Transfer of material to the white dwarf. A significant portion of the expelled material from the red giant is captured by the white dwarf's gravity. This transfer of material plays a crucial role in the recurrent nova eruptions that occur in TCRB. Key points. The red giant's composition is dominated by hydrogen and helium. With a core of helium and heavier elements like carbon and oxygen, it's constantly losing mass, transferring material to the white dwarf companion. This transfer of material is the key trigger for the nova explosions that make TCRB so unique. Understanding the composition of the red giant in TCRB is crucial for comprehending the complex processes that drive the nova eruptions and the evolution of this fascinating binary star system. The white dwarf in the Corona Borealis system has a fascinating composition shaped by its unique evolution and its relationship with its companion red giant star. Primarily, the white dwarf is composed of carbon and oxygen. These are the remnants of the star's core after it exhausted its hydrogen fuel and shed its outer layers. Carbon and oxygen are the ashes left behind after the nuclear fusion process that once powered the star. Degenerate matter. Unlike ordinary matter, the material inside a white dwarf is incredibly dense and exists in a state called degenerate matter. In this state, electrons are packed tightly together, preventing further collapse due to gravity. Accumulation of material from the red giant. The white dwarf isn't just a static object, it's actively accumulating material from its companion red giant. This material primarily consists of hydrogen, the most abundant element in the universe. Hydrogen is continuously pulled from the red giant's atmosphere onto the white dwarf's surface. Helium, a byproduct of hydrogen fusion. Helium also accumulates on the white dwarf's surface. Trace elements. In addition to hydrogen and helium, other elements present in the red giant's atmosphere, such as carbon, nitrogen, and oxygen, can also be transferred to the white dwarf. The layered structure. This accumulation of material leads to a layered structure on the white dwarf's surface. Outer layer, predominantly hydrogen, with some helium and trace elements. Inner layer, a mixture of helium, carbon, and oxygen. Core, the degenerate core, mostly composed of carbon and oxygen. This layered structure is crucial for understanding the nova eruptions that occur in Coronae Borealis. The nova trigger. As the hydrogen layer on the white dwarf's surface thickens, the intense pressure and temperature trigger a runaway nuclear fusion reaction. This sudden release of energy blasts off the outer layers of the white dwarf in a nova explosion, temporarily increasing its brightness by thousands or even millions of times. After the explosion, the process begins anew, with the white dwarf gradually accumulating more material from the red giant, setting the stage for future nova eruptions. The composition's impact. The white dwarf's composition plays a crucial role in determining the characteristics of the nova eruption, such as its brightness, duration, and the elements produced during the explosion. By studying the light emitted during the nova, scientists can gain valuable insights into the composition of the white dwarf and the processes involved in the explosion. White dwarf in Corona Borealis is a complex and dynamic object constantly evolving as it accumulates material from its companion red giant. Its unique composition, shaped by the continuous interplay between the two stars, is the key to understanding the spectacular nova eruptions that make this star system so fascinating. The 2024 nova of Coronae Borealis, a glimpse into cosmic impacts. The anticipated nova explosion of Corona Borealis, TCRB, in 2024 promises to be a celestial spectacle. But what potential impacts could this event have on our understanding of the cosmos and beyond? Let's explore the scientific, technological, and even cultural implications of this upcoming outburst. 1. A deeper understanding of stellar evolution. Novae as laboratories. TCRB's recurrent nova offer a unique opportunity to study the intricate dance of binary star systems and the processes that lead to these explosive events. Each nova eruption provides valuable data on the composition, structure, and evolution of white dwarfs and their companion stars. White dwarf evolution. Observing the 2024 nova could shed light on how white dwarfs accrete material from their companions and how this process influences their long-term evolution. It could even provide clues about the ultimate fate of white dwarfs, whether they fade away or eventually reach a critical mass and explode as a supernova. Unraveling the mysteries of nucleosynthesis. Cosmic alchemy. Novae are cosmic alchemists, creating new elements through nuclear fusion during their explosive outbursts. By analyzing the light emitted during the 2024 nova, scientists can determine the abundance of different elements produced, contributing to our understanding of how elements heavier than hydrogen and helium are formed in the universe. Building blocks of life. Novae are responsible for creating many of the elements essential for life, such as carbon, nitrogen, and oxygen. Studying TCRB's nova could provide insights into how these elements are dispersed throughout the galaxy and how they might have contributed to the formation of planets and life itself. 1. Advancements in astronomical observation. Testing theoretical models. The 2024 nova will allow astronomers to test and refine their theoretical models of nova eruptions. By comparing observations with predictions, they can identify discrepancies and improve their understanding of the underlying physics. New observational techniques. The event will likely spur the development and refinement of observational techniques as astronomers race to capture the most detailed and comprehensive data from the eruption. This could lead to advancements in telescopes, instruments, and data analysis methods. 1. Implications for technology and society. Radiation exposure. While the 2024 nova poses no direct threat to Earth, it's a reminder of the potential impact of high-energy radiation from space on our technology and infrastructure. Studying this event could help us develop better protective measures for satellites and other space-based assets. Space weather. Prediction. Novae and other stellar explosions can influence space weather, which can affect communication systems, power grids, and even astronaut safety. Research on TCRB's nova could improve our ability to predict and mitigate the effects of space weather. Inspiring public engagement. Celestial spectacle. The 2024 nova offers a rare opportunity for the public to witness a dramatic celestial event with the naked eye. This can spark curiosity and interest in astronomy, encouraging more people to explore the wonders of the universe. Citizen science amateur astronomers can play a crucial role in observing and reporting their findings of the nova, contributing to scientific research and increasing public participation in scientific discovery. Potential challenges and uncertainties. Timing and brightness. The exact timing and brightness of the 2024 nova are uncertain. While predictions suggest it will be visible to the naked eye, the extent of its brightness and duration could vary. Limited historical data. TCRB has only had 2 recorded nova eruptions in the past century. This limited data makes it difficult to precisely predict the characteristics of the upcoming event. Unforeseen impacts. There could be unforeseen consequences or discoveries associated with the nova that we haven't anticipated. This is the nature of scientific exploration. We often uncover surprises along the way. The 2024 nova explosion of Coronae Borealis is a unique and exciting opportunity for scientific discovery, technological advancement, and public engagement. By studying this event, we can gain valuable insights into the mysteries of stellar evolution, nucleosynthesis, and the potential impacts of space weather. It's a reminder of the dynamic and ever-changing nature of our universe and the importance of continued exploration and research. The future of Coronae Borealis research, unveiling the secrets of stellar explosions. The anticipated 2024 nova explosion of Coronae Borealis, TCRB, marks not only an exciting astronomical event, but also a pivotal moment in the ongoing research of this enigmatic star system. As we stand on the cusp of this celestial spectacle, let's delve into the promising avenues for future research and the potential breakthroughs that await us. A multi-wavelength extravaganza. The 2024 nova presents a unique opportunity to study the eruption across the electromagnetic spectrum, from radio waves to gamma rays. By observing the nova in different wavelengths, scientists can gain a comprehensive understanding of the explosion's dynamics, the composition of the ejected material, and the physical processes that drive it. This multi-wavelength approach will help answer fundamental questions about how novae generate and release energy, how they create new elements, and how they impact their surrounding environment. Unraveling the pre-outburst puzzle. One of the biggest mysteries surrounding recurrent novae like TCRB is what triggers their eruptions. Detailed observations in the lead-up to the 2024 nova could reveal crucial clues about the buildup of material on the white dwarf's surface, the changes in its temperature and pressure, and the eventual ignition of nuclear fusion. This could lead to better models of nova eruption mechanisms and improve our ability to predict future outbursts. Probing the aftermath of the nova explosion is just as fascinating as the eruption itself. Scientists will be eager to study the expanding shell of gas and dust, analyzing its composition and dynamics. This will provide insights into the elements created during the explosion, the distribution of these elements in space, and the impact of the nova on the surrounding interstellar medium. Unleashing the power of citizen science. The 2024 nova offers a unique opportunity for amateur astronomers to contribute to scientific research. By observing and reporting their findings, they can provide valuable data that complements professional observations. Citizen science initiatives, such as those organized by the American Association of Variable Star Observers, AVSO, are already in place to facilitate this collaborative effort. New observational technologies. The anticipation of the 2024 nova is driving the development of new observational technologies and techniques. Astronomers are refining their instruments, telescopes, and data analysis methods to maximize the scientific return from this event. This could lead to breakthroughs in our ability to study transient astronomical phenomena and deepen our understanding of the universe's dynamic nature. Broader implications for astrophysics. The insights gained from studying the TCRB nova will have far-reaching implications for our understanding of astrophysics. The knowledge acquired can be applied to other types of stellar explosions, binary star systems, and even the evolution of galaxies. It could also shed light on the formation of elements in the universe and the potential impact of novae on the habitability of exoplanets. Public engagement and inspiration. The 2024 nova presents a unique opportunity to engage the public and inspire a new generation of scientists and astronomers. The spectacle of a visible nova eruption can captivate imaginations and spark curiosity about the wonders of the cosmos. Educational outreach programs and citizen science initiatives can leverage this interest to foster a deeper appreciation for science and its role in understanding our universe. The future is bright. The future of research on Corona Borealis is bright and full of promise. With advancements in technology, increased collaboration between professional and amateur astronomers, and a growing interest in the public, we are poised to unlock the secrets of this enigmatic star system and its spectacular nova explosions. The 2024 nova will undoubtedly be a watershed moment in the study of TCRB, providing a wealth of data and insights that will shape our understanding of stellar evolution, nuclear synthesis, and the broader cosmos for years to come. Let's keep our eyes on the sky and anticipate the exciting discoveries that await us. Please press the like button, share and comment the video, and please do not forget to subscribe for more videos.